Hello, in this video we are going to go over integration, specifically the area and the definite integral. And first, to begin with, we can look at the approximation of area, which is one of the most widely used applications of integration to find the area underneath a curve, such as in example 1 here, to consider the region bounded by the y-axis, the x-axis, and the graph of f of x is equal to the square root of 4 minus x squared. And here from this graph we want the area then of this entire blue shaded area here. All of this. And the first way we could approximate this is by using, in this case, two rectangles, where the height of the rectangle is the value of the function at the left endpoint. So, for example, this first rectangle would have height f of 0. The second one will be f of 1. We could calculate f of 0 to be 2, f of 1 to be the square root of 3. So the area multiplies, since the width of each of those rectangles is 1. I'm going to take 1 times f of 0 plus 1 times f of 1, which, once we do that, we get 1 times 2 plus 1 times the square root of 3 to get 2 plus the square root of 3, which approximates to about 3.7321 square units. We could repeat the same exact example now using the right endpoint. So in this case we have f of 1 for the first rectangle, but now using the left endpoint of the second one is going to give us this f of 2 is equal to 0 here. So now we get 1 times f of 1 plus 1 times f of 2, which once we calculate that we just get square root of 3 since f of 2 is just 0. So now our approximation is 1.7321 square units, which is a relatively big enough difference, right? We can again repeat it by now finding the midpoint of each interval to determine the height of the rectangle. So our first rectangle here between 0 and 1, using the midpoint of where it touches the curve here, and finding that function value is going to be the height of this first rectangle. And again, the same thing about the height of the second rectangle. So we're doing 1 times f of, in this case, 1/2, due to, again, using that midpoint formula, and plus 1 times f of 3/2, again, due to that midpoint rule. This makes 1 times the square root of 15 over 2, plus 1 times the square root of 3 over 2, which is about 3.2594 square units. Then again, we could repeat it again now, this time increasing the number of rectangles, in this case 4. So our area now will constitute now using a width now of 1/2 as opposed to 1. So 1/2 times f of 0 plus 1/2 times f of 1/2 plus 1/2 times f of 1 plus 1/2 times f of 3/2. We multiply and add all that together to get 3.4957 units, which in this case now is going to be a better approximation. And then finally we can repeat it again using 8 rectangles. And now we have a width now of 1/4 since we have 4 rectangles in each interval. This will be 1/4 times f of 0 plus 1/4 times f of 1/4 plus 1/4 times f of 1/2 plus 1/4 times f of 3/4 plus 1/4 times f of 1 plus 1/4 times f of 5/4 plus 1/4 times f of 3/2 plus 1/4 times f of 7/4. Multiply all that and add all that together to make 3.3398 square units, which now is an even better approximation. This, though, can be generalized to divide the area between x is equal to 0 and x is equal to 2 to n equal intervals or parts with a certain width, in this case of 2 minus 0 divided by that number of parts or intervals that we want. Our function y is equal to the square root of 4 minus x squared. We can rewrite that by squaring and adding to make x squared plus y squared is equal to 4, which would be a circle with a center of 0, 0, and a radius of 2. The quarter of the circle from example 1, so that was this graph, where we had a fourth of the circle here, so it's at a radius of 2. Since we have that quarter of the circle from example 1, we could calculate its area directly by using the area of a circle and taking a fourth of it. In this case, using a radius of 2, we have 1/4 times pi times 2 squared. That just simplifies down to pi, and our exact area is 3.1416. Right? And we could try to approximate the area using, again, those rectangles, finding the approximations for it. And if we take the left sum and increase the number of parts or intervals that we're looking at, we do start getting close to 3.1416 by the end here to 500 parts, but not exactly. Just at the right sum, if we start going all the way down here, it will start approaching it, but as you could see though, based upon this 500 parts, the right sum is going to underestimate that area, and the left sum overestimates it. We could take a trapezoidal approximation, which just averages these two sums, and that does get close to 3.1416 here by the end, but again, it's not exact. If we use the midpoint rule that we saw in the previous slide, by the time we get up to 500 parts, notice we have our area approximately equal to the area that we calculate up here, which we can generalize to the idea of taking the limit as n approaches infinity, or again gets very large, since 500 parts is very large. The limit as n approaches infinity of the sum of the areas of all those n rectangles. That is going to, when we take the limit of that, it's going to equal to pi, which is exactly what our approximation is equal to from the area of that quarter of a circle. And again, we could further generalize it, since our example had specific parts. We could generalize it for any area between two endpoints for any curve. Doesn't matter what the curve is. In this case, if we have between A and B being our endpoints, then the width of each of those rectangles is going to be this delta x, which is b minus a over n. Okay? And we could see that, based upon the number of rectangles that we want, so in this case we would take that b minus a and divide by that number of rectangles of equal width. So here, if we have a relatively small amount, we get a small number of rectangles, but then if we take an even larger amount, see how it approximates that curve a lot better than picture A here does, since we have all this white space in here. This second picture minimizes that white space. The area of each of these rectangles is going to be the value of the function at the particular width that we want, the particular value of the function times the width. And we refer to it as the ith rectangle, since we're just choosing one of the rectangles to calculate the area for. We could do the area of all n rectangles by taking the sum from I is equal to 1 to n of the value of the function for each of these rectangles times the width. So again, delta x. The exact area for the number of rectangles increases without bound, presuming the limit exists. This becomes the limit as n approaches infinity of that sum from I is equal to 1 up to n of the value of the function at each of those rectangular pieces times the width delta x. Okay? And that is the approximation of this, which would then lead us to defining the definite integral. And we could calculate the definite integral using this formula. So the definite integral is if f is defined on some closed interval a comma b, that definite integral of f from a to b is given by, again, the integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum of I is equal to 1 to n of that function evaluated at each of those rectangular pieces times the width of delta x, provided that limit exists, where delta x is b minus a over n, and x sub I is any value of x in the ith interval. And this is an example of a Riemann sum, which was, in this case, discovered by a German mathematician named George Riemann in the, I believe in the early 1800s. Yep, early 1800s. And from this definition, we have our upper limit or bound to be b, and our lower limit or bound to be a. Now, mind you, we could always do these calculations using a by hand method, but we could also do it on a calculator. So for example, let me just show how to do it using a TI-84 color edition. Let me pop that up here on the screen. In this case, this. And put the LCD up. Okay. So, in order to calculate these on a graphing calculator such as the TI-84 plus C, we could go to where it says math here and go all the way down to number 9 here. That's one that says function integral. And then here we could type in the integral that we want. So the one that we were just doing, which went from 0 to 2 of the function the square root of 4 minus x squared. And we want this integral with respect to x. And if we do this calculation, we should get approximately pi. And if we hit enter, we do indeed get pi, 3.141593074, an approximation of our value for pi. But continuing on from that, our second example is we want to approximate the integral from a to b of 2x dx, which is the area of the region under the graph of f of x is equal to 2x, which I have that graph down over here, above the x-axis between the values of 0 and 4, by using 4 rectangles, which we have spaced out as such here on the graph, of equal width whose heights are the values of the function at the midpoint of each interval. The width of each rectangle, then, since we have, endpoint of 4 and 0, so 4 minus 0, divided by the number of rectangles we want of 4 makes 1. And we have at each of those values, at each of these values here, we could calculate the midpoint from each of these rectangles. So this first one would have a midpoint of a half, and the value of that function at a half is 1. Likewise, for 1.5, that's going to be 3, 2.5, 5, and 3.5, 7. So we could take the sum of each of those function values times the width. So in this case, we have f of 1/2 times 1 plus f of 1.5 times 1 plus f of 2.5 times 1 plus f of 3.5 times 1. If we multiply and add, we get a value of 16. And once again, we could certainly calculate the exact area, right, since underneath that line 2x, we would have a triangle. We could take the area as 1/2 times the base times the height to get a half times 4 times 8, which again makes 16. So our exact area is indeed the calculation that we obtained from our integral formula. And we could also do this as another method on the TI-84 plus color addition calculator as well. So let me go back onto that calculator. And for this one, once I open up everything, and let me clear these as well. Alright, so for this one, we could go and do the calculations on a calculator nicely by going into the stat menu in here and clicking on edit. And on here, we could create a whole bunch of lists. So in this first column here of L1, we could put the number of rectangles that we want, starting from 1 up to 4. So type 1, 2, 3, and 4. Then for the second column on here, we can navigate over and go up to the top where it says L2 and type in the following formula, since we want the midpoint of each of these areas. So in order to find those midpoints, we could take whatever the value is of L1, right? So we would need to go for this second stat, hit L1, and we want to subtract from that 0.5 in order for us to get the midpoint of each of those rectangles. And then by hitting enter, it automatically does that for us. I mean, again, we could type that in manually, but this is a way to do it quicker, especially if you have a lot of rectangles. But these are those midpoints that we want to evaluate the function at. Then for L3, let's move over to there, navigate up to that. We can then, for this one, take the value of L2 and multiply that by 2. So we would have 2 times, again, second stat, and we want L2 this time. And again, hit enter. And we could get each of those function values. And then in order for us to get the sum of all of these values, we are going to need to go to, this should be under here, stat, second stat, and then we need to go over to math, and then choose option number 5 on here. So in that case, the function of sum, and not in the list mode. Let me get out of that. In the regular calculator area here, we are going to go to second stat, click the right arrow twice to go over to math, and choose option number 5, so sum. And we want to get the sum of, again, second stat, in this case L3. So that was number 3 on here. In order for us to find the value when we add each of those parts, clicking enter will give us the value that we got on our example, which was 16. So, moving back over then, we have an application of this definite integral formula that we just had as the total change in f of x, where if we let little f of x given the rate of change of big F of x for x in a closed interval a comma b, then the total change in big F of x as x goes from a to b is given by this limit formula, which is the limit as n approaches infinity of the sum from I is equal to 1 up to n of the value of the function at each of those rectangular pieces times the width of each piece is equal to the integral from a to b of f of x dx. And from here we'd have this example. So the graph down here that I have right here, this graph shows the rate that oil is leaking from a machine in a large factory in cubic centimeters per hour with specific rates over a 12-hour period given in this table. We want to approximate the total amount of leakage over a 12-hour shift. So since we have 12 hours, each of these widths here is going to be 1, as you could tell from our graph, and also on the table. So we are going to multiply each of these function values by 1 for the area, as we did here in the formula. Now when we multiply all those and add them together, we should get a value of 187.8, which, as an interpretation of this scenario, is about 187.8 cubic centimeters of oil leak during this 12-hour time period. And as such, we can write it as the definitive integral of that integral from 0 to 12 of f of x dx is approximately 187.8. And then finally, a driver traveling on a business trip checks the speedometer each hour. The table down over here on the slide shows the driver's velocity at several times. We want to approximate the total distance traveled during the 3-hour period using the left endpoint of each interval and then the right endpoint. So, based upon the left endpoint, since each of these goes up by 1 of the time part of this table, we're going to take 0 times 1 plus 52 times 1 plus 58 times 1 to make 110. Using the right endpoint, we can use 52, 58, and 60 to get 170. But the left endpoint in this case is going to underestimate. The right endpoint overestimates. So we could take the average of the two, the right and the left endpoint. We could take the average of the two, which is referred to as the trapezoidal rule, and that gives us 140 miles, which would be the best approximation of the total distance traveled in that 3-hour period in the example. Thank you.